Okay, Happy New Year to everyone. Welcome to the first lecture in the new year. We will, this lecture and next lecture, we will do a bit Diophantine approximation, Diophantine geometry, Diophantine stuff. And when I prepared this lecture and looked at the exercise sheets, I played around a bit with the new artificial intelligence ChatGPT. Probably most of you know it. And I tested a bit, can it solve the exercise sheets and can it solve things? And it's interesting that sometimes it can really prove something. For example, what we will do in the next lectures is also talk about the algebraic points and the structure of the algebraic points and the torsion points. And it almost correctly answered what the structure of the torsion points of an elliptic curve is, but only almost, but in a way that's not totally absurd wrong. So that was interesting. But on the other hand, sometimes it was totally wrong. So if you use ChatGPT to do the exercises, you should be aware that it's wrong a lot of the time and check the answers. For example, I asked it if every cubic curve is an elliptic curve, and it said no, and gave an example that is an elliptic curve. So not so nice. Okay, we will concentrate on Diophantine approximation. And Diophantine approximation is, I love this subject because it's very, on one hand, sometimes very explicit, and on the other hand, totally vague and ineffective. And everyone's racing to make theorems explicit. That's at least my feeling there. And I love explicit things. But we will only scratch the surface of Diophantine stuff. Okay, so what we did in the last lectures was this to find out about the structure of rational points of elliptic curves, which is basically torsion times the free part. So these are the points with coordinates in Q. Now, if we consider all coordinates, where we allow coordinates in the complex numbers, which is basically the same as allowing coordinates in the algebraic numbers because the curve is an algebraic equation. Then we want to see, what happens then? What is the structure of the torsion points? What's the structure of the torsion points? And in the other direction, I should have left some space up here. In the other direction, it's also interesting to find out what are the points with integral coefficients, coordinates. So of course this will be larger than this, and this will be smaller than this. And we found out in the Lutz-Nagel theorem that those points are all with integer coordinates. So those will be here just like here. And the question is, what from the free part gives us more integer points? So So Lutz-Nagel tells us that all torsion points have integer coordinates, but the other way around is not true. So now the question is, how can we find them? How many are there? Do they have some special structure? Can we construct new points from points that we get that we already have? And if we just look at, so we consider one example. Look at the curve y squared is equal to x cubed plus 3. And in some chapter before, where we computed the torsion groups of the elliptic curves, we saw that this doesn't have torsion points. This was chapter 4, section 3. No torsion points. But if we look at this equation, we see that, yeah, x equal to 1 and y equal to plus or minus 2 is an integer point. 1 plus minus 2 are points with integral coordinates. So there is hope that we can find points with integer coordinates that are not torsion points. So let's think about what would we expect, how many there are. So of course, when the rank is 0, then there can't be more than just the torsion points. So for rank 0, only the torsion points. Have integral coordinates. So it makes sense to only look at curves where we have infinitely many rational points, so where the rank is at least 1. So if we have rank at least 1, we can find a point of infinite order that generates infinitely many points with rational coordinates. Oop. Then we could just take all the multiples of p and see how many of those have integral coordinates. So if we look at the addition formula, we can get a feeling of how probable this is. So if we call the coordinates xn and yn, then xn is this. So even if, when we add n minus p and p, even if n minus p and p have integral coordinates, then there's basically no reason why the point n times p should have integral coordinates, because we divide by something. And there's no reason that this should cancel out. So we get the feeling that integral points are very unlikely. And in fact, that's a theorem that we will not prove, but we will juggle a bit around it. So we will do some things around this theorem that go near a proof, maybe. So this is the theorem by Siegel. Usually everything with Siegel is not effective. So this is also not effective. So let's see. Be a non-singular cubic curve. Integer coefficients, and then C has only finitely many integral points. So here a cubic curve can also mean something that we would still have to transform by a variable transformation into an elliptic curve, but every elliptic curve for this theorem holds for every elliptic curve. So for any elliptic curve defined over Q, we have only finitely many integral points. And as I said, this is not effective, so it doesn't say how many finitely many points or how can we find them. It's not constructive. It only says there are only finitely many. So now we will look at why does this only hold for cubic curves and not for linear curves or quadratic curves. So I will give some examples when it doesn't hold, or maybe counter examples for linear or quadratic. So if we have a linear equation, that's ax plus by is equal to c with a, b, c in z. And if we have one solution, with integral coordinates, then we can construct infinitely many more. So of course, since x0, b, y0, and a are fixed, and only n is going from 1 to infinity or also to minus infinity, then we have that all the points that we get through that are distinct, and if you plug them in, you see that they're all a solution. So if we have one solution, then we have infinitely many, and then in fact all the solutions are of this form and there are no other solutions. Of course, this doesn't say that we always have infinitely many, but we can certainly find some equation that has at least one solution, and then we have infinitely many. So Siegel's theorem doesn't hold for linear equations, and it also doesn't hold for quadratic equations. Yeah, we could also do a whole lecture about equations like this and quadratic number fields, and this would also be a very nice lecture. Okay, so here we have the solution 3, 2. And we can also see here for one solution that we have. We find the following solution. And if we start here with 3 and 2, who are both positive, and we continue this iteratively until infinity, then those are always positive and they are growing, so they are distinct. You can plug them in and see that they're a solution. So in this, repeating this process, we get infinitely many distinct integral solutions. Okay. Okay, so now we will consider one special case of one equation and kind of prove Siegel's theorem there. And yeah. So the story is probably well known. Ramanujan was a famous Indian mathematician, and he got tuberculosis. And he was in the hospital, and Hardy visited him, and he went there with the taxi with the number 1729 and arrived and said to Ramanujan, "Oh, I arrived with this taxi. It has the number 1729. It is a rather dull number, but now here I am." And then Ramanujan said, "Oh, well, no, it is not a rather dull number. It's very interesting. It's the smallest number that can be expressed as the sum of two cubes in two different ways." Yeah, but later Ramanujan died anyway, and but this is the most famous story of those two. So, what does this have to do with us? It is basically this is basically 2 or 4 points on the following cubic. And of course the points on it are 9, 10, 10, 9, 1, 12, and 12, 1. And Siegel's theorem tells us there are only finitely many. There could be more than those 4. And Ramanujan says this is the smallest number such that it has 4 points. So we will talk a bit about why are those all the solutions. So basically Siegel's theorem for this special curve. So suppose we have a solution and even though we will now kind of prove Siegel for this curve, it will be a bit general since we can transfer to some curves but not to all. And you will also in the exercises do this procedure that I will do right here. So suppose we have a solution. Integral solution. So an integral point on this curve. Then so we can factor both sides. And this is also the point. So if we have an equation like this that we can factor, then we can, bless you, then we can use this procedure that I will describe now. If we can't factor the right-hand side, then we cannot use this algorithm. So we factor the left-hand side and the right-hand side. And, well, now we have basically a smaller problem. We can solve now x plus y is one of the factors, and this is the other one of the factors. So we have to solve x plus 1 is equal to a, and x squared minus xy plus y squared is equal to b. Oops. Where a times b is 1729. And yeah, we have to do this for all possible factorizations. So a is either 7, 13, or 29, or 7 times 13, or 7 times 29, or 7 times 13 times 29. So we do this. Oh, and so basically before we do this, we can also solve this for x or for y and substitute it in the second equation. So this gives that y squared minus x times a minus x plus a minus x squared is equal to b. this is 2x squared, 3x squared. This is minus 2 and minus a, so this is a plus 2 times x plus a squared is equal to b. Is this correct? This is 2a, so this is 3a. Oh, I have a minus here. There's a minus. There's a minus, yeah, okay. This should be correct now. 3x squared minus 3ax plus a squared is equal to b. Okay, so we can just use the PQ formula or some formula for solving quadratic equations. And this will be integral if this is integral. Okay, so we just have to check this for all possible combinations of a and b, where a times b is 1729. So we try this out. Try for a, b, 7, 13 times 29, 13, 7 times 29, 29, 7 times 13, 7 times 13 and 29, 7 times 29 and 13, and 13 times 29 and 7. Yeah. Okay, yeah, so we have everything. Okay, I will not work this out, so assume we tried this, and then we find out for a equal to 13, b equal to 7 times 29, and a equal to, oh, I wrote 19 here, but this is probably 29. A 29 and b 7 times 13. We get integral solutions. Let me just check if this 29 is correct. It also says 19 here, but this is this a, this is a 19, sorry. So these are all 19s. So this is also a 19. Okay. Yeah. Okay, so for those combinations we get integral solutions. And if we now plug it in here, here, or yeah, well, we plug it in here, and then see that yeah, that they just lead to the solutions that we found. We get integral solutions 9, 10, 10, 9, 1, 12, and 12, 1. Or, well, basically just the one solution, and if we just switch x and y, yeah?
Don't you need to check for negative a and b, and also a equals 1 and b equals?
Oh yeah, a equals 1 and b equals, Yeah, and the negative, we also need the negatives. Or do we already have them? No, we also need the negatives. Yeah, thank you. And of course I forgot 1. So 1 and 7 times 13 times 19. 7 times 13 times 19 and 1. Yeah, thank you. Yeah, so this gives our 4 solutions. And here we also prove that those are all the solutions that we can have. Because if we have another solution for this equation, it would have to factor in one of those ways in order for those coordinates to be integral. So in this case, we proved that we only have finitely many, and we also just found all the 4. So it's effective, constructive, as we like it. We can do this every time that we can find a factorization, because the cubic is always of degree 3. So if we have a factorization, one is linear and one is quadratic, so we can use one to substitute y or x in the other one, get a quadratic equation, solve it, and then just go through the list of possible a and b. So this would raise the question, we could look at general equations of the type x cubed plus y cubed is equal to something. And that's what we will do now. Well, I'm much faster than I thought. I'll try to slow down a bit. Okay, so in this case, where we can factor the cubic, we could ask ourselves, what can we say about this case? So we still take x cubed plus y cubed is m for some, I think we only take positive m. Or maybe we also allow negative m. No, positive m. Okay. So we take this cubic, and the question is, can we bound the size of the solution by m? So not the numbers of solutions, the number of solutions, so how many, but the size of x and y. Why would we like to do this? Because then we can use a computer to run through all the possible x and y coordinates and get a solution in hopefully finite time. Okay, so in our case here we can, we have a cubic here that factors, so and B okay, now we can play around a bit. So B is a divisor of M, so we certainly have that M, or that B is at most M. So B is this. And now we can just play around a bit and take 1 over 4 x squared and take it with this part. So this is 1 over 2x minus y squared. And we don't need the triangle equality actually. So this is positive, this is a square, so this is at least 3 over 4x squared. And we bounded already x in terms of m. Okay, and this is symmetric in x and y, so the same holds for y. Yeah, okay, and the same for y. Okay, this is already very nice. Still, we cannot say anything about the number of solutions. Yeah, let's look at another example to proceed further on that question. So consider this cubic, and we can, with a variable transformation of, okay, this is capital X, we can turn it into y squared x cubed minus 48. And that's also one thing I asked the ChatGPT. So I gave it this equation and asked, can you find a variable transformation to transform this curve into this one? And it said, no, there is no such transformation. And then the first thing I asked is, can you turn this by a variable transformation, by a rational variable transformation into Weierstrass form? And it said no. And then I gave it this form, and it still said no. And then I also gave it the variable transformation, and then it said yes and proved it. So it can be helpful, but you shouldn't rely on it. So on this thing, we have an integral point. This is wrong. Minus is minus. Okay. Here we have the integral point minus 1, 2. And if you want to find out which point it is on here, then we just use this, and we get that it corresponds to 4, 4. There's an integral point on her. And corresponds to 4, 4 on y squared is equal to x cubed minus 48. And now we just compute some multiples of it. So 2 times 4, 4 is 28 minus 148. Okay, this is another point with integer coefficients. 3 times 4, 4 has denominators. Okay, but well, still we find one point, and since 3 times this point has denominators, it has infinite order. And then also, of course, the original point has infinite order. So, well, at least we found 2 points of infinite order, so no torsion points with integral coefficients. And the curve has rank at least 1. So say we have n different points. Capital N rational points. P1 to Pn. And we just write it like this in Low's terms. We have this one point and we write it in Low's terms. Still on this curve here. So if we have this on this curve, then it means that a cubed times d cubed plus c cubed b cubed is 9 b cubed d cubed. So just any point here on the curve. Now if we sort it a bit, then we see that one moment. So I have to write it like this to see everything. Okay, so now here we have this B3, and this means that B3 divides b to the 3b cubed divides a cubed times d cubed. Cubed d cubed, and this means that d cubed divides c cubed b cubed. But a and b are co-prime, so b cubed divides d cubed, and c and d are co-prime, so d cubed divides b cubed, so they are the same. And what does that help us? We do this now with the n rational points that we found here, that we just suppose that we have, and write pi ai over di, bi over di. So I just oh wait, CI. So I just substituted B by D because we showed that they are the same. And we write it like this, with positive DI. And if we now choose our M, so we had this example with this 9, but if we look at the general cubic here, or the a bit general cubic here, where we just have this M, and choose M to be 9 D1 until dn cubed. So these di are just the denominators of the points. And if we then take all the points and multiply by the product of the di, new points, pi prime, where we multiply denominators by d1 until dn, then then we get a point on the new curve, or then we get points. Oops. So this may sound a bit out of the context, but what does it tell us? It tells us this proposition. Oh, sorry. Maybe like this. That for every n. Oh, and I said, now say we have capital N rational points. These are just, these can just be constructed from the fact that we found this for 4 point on the elliptic curve y squared is x cubed minus 48, which has infinite order, so we can produce arbitrarily many distinct rational points. And then we can take them and go back with the variable transformation to the cubic x cubed plus y cubed is equal to 9. And then we can do all those calculations. And then we have for, this, where, yeah, okay. Yeah, then we have for an arbitrary n, then we have found a curve that has n points. So for every capital N at least 1, there is an m at least 1, such that this cubic has at least n points with integral coordinates. This is, well, of course this is nice. We have something constructive and also explicit in the way that we say we want n points with integral coefficients, and then we get n points, and this n is just a natural number. But it feels a bit like cheating, because we constructed the points and then invented a curve. And it's not that we are given a curve and we can say we have that many points, we can construct at least that many of them, and here they are. It's just a bit like going backwards. So this is not very, this is not making me happy. And what we, so we did now several things, and everything is not quite what we want. What we would really like would be that someone gives us an elliptic curve, and we say, okay, it has a 37 integral points, and I can compute at least 10 of them, and here they are. But unfortunately, none of what we did helps us with that, but helps us with that specific problem. But it shows that we can do things that are also nice, and the original problem is very hard. We will also still get to the problem and get to the Diophantine approximation part, but now we will take a break until 11:15. And